Hello, and welcome to another adventure in the world of physics. We're going to be talking about simple harmonic motion today, but before we get there, let's just analyze the behavior of a dot as it orbits around in a circular path. Alright, so as you look at this animation, nothing special so far. But if we break it down into its horizontal and vertical components, we're going to start to see a pattern. First, let's observe the amplitude of this circle as it orbits around. Initially, it starts off at a value of 0, and as it starts to orbit, it's going to increase all the way up to a maximum value of its radius, also known as A. And as time continues forward, it's going to drop down to a value of 0, and then it'll reach to a value of negative A. Alright, let's animate it out and see what happens. Have you seen that type of curve before? That's right, it's called a sine wave. We can also repeat this again in the x dimension. Now this time around, you'll notice that it starts off at the value of A, and as time goes by, it's going to drop down to a value of 0, then negative A, back to 0, and it'll repeat itself over and over again like so. Lovely, it looks like another wave. Now this one over here isn't a sine wave anymore. It's very similar to it. It's just shifted by about 90 degrees. Right? So this one here is known as a cosine wave. And in general, we often use this as our base function. If you're wondering why is there all this weird stuff inside here, it's because often when we measure angles in physics, we don't measure it in degrees anymore. We measure it in radians. And that's why there's this whole 2 pi thing going on. More about that later on. Before we get there, let me show you another cool demo. There's a scientist who attached a spray paint can to a spring and decided to let it oscillate up and down. And let's take a look at what the outcome of it is. What you know about rolling down in the deep when your brain goes numb? You can call that mental freeze. When these people talk too much, put that stuff in slow motion, yeah. In slow motion, yeah. Pretty cool, huh? We see that it is a sinusoidal wave. So, we're going to go off and convert between that formula there and eventually get down to this. One of our 2 main formula for today's lesson. Okay, so how do we get from there all the way down to here? First off, you'll notice that as the spring goes up and down, it more or less represents either the horizontal or the vertical components of a circle, or of an object going around in a circle. And the reason why it's going around in a circle is because there's this force called the centripetal force acting on it, trying to return it back to the center. And the formula looks like this. Now we also know that it's a spring that's physically trying to bring it back to its rest position, so we know that that force is equal to k delta x. So the spring is exhibiting more or less centripetal force, just in one dimension only, and so we can flatten this 2-dimensional problem into a 1-dimensional solution by equating them together. One thing just to point out, this amplitude over here, yes, that's the radius, it's also r delta x. So that's why we can replace delta x with the value of r. That way when we equate them together, the 2 r's divide each other out. If we bring t squared up and k down below, we end up with something that looks like this. And lastly, when you square root both sides to isolate for t, pi squared drops down to pi, 4 drops down to 2, and you're left with this formula here. So that's how this formula is derived. Let's go through a sample problem now. What is the spring constant of a 500-gram spray can that's being suspended on a spring and it oscillates up and down 1.5 times per second? You can pause the video and try it out yourself. Did you get to the answer of 44 newtons per meter? If you did, excellent. Alright, let's solve this together. One thing as a reminder is that period and frequency are inversely correlated with each other. So in other words, t can also be represented by 1 over f. Next, you can take this formula here and slowly isolate for the variable k. We do that by bringing 2 pi over, so we have 1 over, oh actually, Yeah, I'll start off this way. 1 over 2 pi f is equal to the root of m over k. To get rid of the square root, we square both sides. So we have 1 over 4 pi squared f squared is equal to m over k. We bring k over to the left-hand side, so we have k is equal to m times 4 pi squared f squared, and that's how we get to this state over here. Sub in all the values, and if all goes well, you'll reach 44 newtons per meter.
I will try to hold my body as horizontal as I possibly can in order to be at the same level as the bob. I will start when I come to a halt here. There we go. No! You count. This hurts.
He's a pretty fun professor, and he's trying to prove to you that you can mathematically determine the period of the pendulum. All right, so you calculate it out with a very small error, and let's go through that. Effectively, he's trying to prove this formula here. Okay. Now, just to show you how to solve these type of problems, well, as long as the angle is within 15 degrees, this formula here is valid. All right, and that's why we call this a simple harmonic motion, because we're trying to simplify things by making this assumption here. Anyways, let's just describe what all these variables mean. L is for the length of the string. Sometimes it's lowercase l, sometimes it's capital L. G is for the planet that you're on, the gravitational field strength. And T, as before, is the period. Try out this problem. Did you get to the answer of this? If you did, excellent. For tonight's homework, work through these questions over here. And no, this video is not over yet. I just shown you the formula here, but it is pretty neat how we derive out this formula. All right, and it's known as this thing called a small angle approximation. It's the only way to figure out these problems here. So as long as your theta is less than 15 degrees, this formula works out beautifully. Let's go through the proof. We go back to the lovely circle again. Now, circles can be described in different ways, all right, or the angles within a circle. Most simply, we usually start off on the right-hand side and call it either the 0 degrees or 360. And as we orbit around counterclockwise, by the time we reach this lovely angle over here, that's our 90. After we go halfway through around the circle, we've reached 180 degrees. And by the time we reached full circle, we've reached 360 degrees. Now, if we had a line that was inside here, and it tried to scribe out its circumference, we know that the circumference is going to be equal to this formula here. So delta x, the length of the circumference, is equal to length times the angle that you multiply by. Now that seems rather odd. Why are we writing out like this? Well, it's because often when we measure angles in science, we don't use this system anymore. Instead, we have a different system that's called radians. And this is how it works. As you may know, if you go all the way around a complete circle, you have traveled a total of 2 pi times the radius. In this case over here, we replaced radius with the letter L. All right, so delta x is equal to 2 pi times L. And we use this because now we don't need to deal with this weird, obscure angle over here, such as 360 degrees. I mean, where did they get that number from? How does a full circle work up to 360? It's a arbitrary number, and they could have even used a metric value of 100. Therefore, by the time you reach up here, you get 25, and so on and so forth. In fact, there's a similar system like that, and it's called gradients, where here you're at 0 grades, here you're at 100 gradients, here you're at 200, and by the time you go full circle, there's the metric equivalent. All right. But again, when you go around a full circle, since it's equal to 2 pi times the radius, well, then why not just call the full circle pi? So if you go through a full circle and it's called 2 pi, then half a circle is pi, and a quarter of a circle is pi divided by 2. And that's how we're able to find out the path of the arc. All right, so the path of the arc, or the circumference, is equal to the radius times the angle measured in radians. We can correlate that with regards to our pendulum as well. This time around, our pendulum is L. The angles here are the same that we're referring to. And here is our path of arc, delta x. Now, if we keep the angle relatively small, then we can approximate out the length of x. All right, so sine of theta is equal to the opposite over the hypotenuse. Now, clearly, these two lengths are not the same, but they are roughly the same as long as you keep the angles relatively small. What I have here on the right-hand side is a chart converted between degrees and radians. How do you do that? Well, you know that for every 360 degrees, it's equal to 2 pi. So by using that conversion ratio, you can create out this lovely chart here. Now, there may not appear to be any pattern so far, but if you decide to do the sine of 0 degrees, the sine of 1, the sine of 2, so on and so forth, you end up getting this chart over here. And here's where the neat things start to happen. All right. Now, even though the sine of 7 gives you this weird decimal number, if you convert 7 into a radian value, hey, look at these two values now. They're pretty close. In fact, they're pretty close until you get to around 15 degrees, and that's where there's a bit of deviation. If you try to calculate out the percentage error, here's the lookup table for that as well. All right. So if you want to be less than 1% in your error, you pretty much want to be less than 15 degrees. And as long as you guarantee that, this formula over here can be simplified down to this. Okay, so why are we doing this stuff right now? Well, let's go back to this diagram one more time. Effectively, we have a mass, and the mass is being restored by a component of gravity. Effectively, this behaves kind of like a banked turn, where there's two components to the object for its force of gravity. There's the inline component, and there's the perpendicular component, which competes with the normal force, which is caused by the tension on the rope. Since we're only concerned about the restoring force, or the force bringing it back to its rest position, we're only concerned about this part here. So our F net in our x dimension is equal to the sine of mgl. Sorry, the sine of mg, no L. We've also argued that as long as you keep the angle within 15 degrees, this formula here is approximately true. So we can replace delta x, you can replace sine of theta with delta x over L. This is a restoring force which allows it to start to pendulate back and forth, kind of behaving like a spring. So if it behaves more or less like a spring at very small angles, we can equate these two equations together. The delta x's divide each other out, and if we bring the k downstairs and the L upstairs and the g downstairs, we end up with this relationship here. So as long as theta is less than 15 degrees, we exhibit something known as simple harmonic motion. I know, simple, but the derivation is rather complicated. But it gets us to this idea. If m over k is similar to L over g, then we can take this formula up here and replace the L over g with m over k. Or sorry, replace the m over k with the L over g. I don't think I'll be editing this, but I hope you get the idea that this is the derivation of how the formula is created. All right, so your homework is still the same as before. To finish off with this, here's a lovely video.
Okay, you're being recorded.
Hey, you having fun right now? You know what's also fun? Something called SHM. Yeah! Look at that. SHM, for simple harmonic motion. What does it mean? Well, if you get lazy with your calculations and you're only 15 degrees from your rest, the period they experience right now will be pretty much the same as the period experience right over here as well. I kid you not. Let's back it up by doing some analysis. And there you have it. SHM.
Have fun with your homework.